Hello, and so we had some questions, or had a question about just trying to go over simplifying radical expressions and also solving radical equations. Okay, so I'm just going to go through some of these problems here. You can see that I listed at the top of the page here the section number, the page number, and the problem numbers too, if you want to kind of reference them in the book. Okay. So directions for number 7 here are we are supposed to simplify the expression by writing it using rational exponents and then using the properties of rational exponents, simplify it more, right? Assume all variables are positive, which is good because, if you want to take the square root of like a negative number or anything like that, exponents in simplified form should all be positive. And that's a typical rule where you want to leave exponents to be positive in simplest form. Okay. So looking at what we have right here, we're supposed to first convert these radicals, right, to rational fraction exponents. So when you have a fourth root, right, that is the same thing as rewriting that as the fraction 1/4, right? So 25 to the 1/4 instead of the fourth root of 25. Likewise, the cube root of 5 becomes 5 to the 1/3. Okay, so far so good, right? We wrote it in rational exponents. Now we want to try and combine these. However, we have different bases, right? Our properties for exponents only work if we have the same base, right? So we need to get a common base. Well, 25, we can rewrite that as 5 squared. And bring down that other 5 to the 1/3 there. And now we have a power to a power here. And when you have a power raised to another power, right? An exponential raised to another exponent, you can multiply the powers to simplify. So in other words, we get 5 to the 2/4 power there. And we still have 5 to the 1/3 power here. Okay, and of course you might look at that and say, Mr. Witt, 2/4, we can simplify that fraction. And you're right, we can. So I'm going to go ahead and change that to 1/2. Okay, and now we have a common base. They both have the same base of 5, which when we multiply, so here we had power to a power, so we ended up multiplying to get that new power there. But when we multiply the bases that are the same, we add these exponents. Okay, so notice the difference here. It's an exponent raised to another exponent. You multiply those two exponents. When you are multiplying the same base, okay, you then add these exponents. Right? I mean, think about it. This back to like basic stuff, right? If you have x times x, what's that? It's x squared. Why? Because it's x to the 1 times x to the 1. You add the 1's together, and you get the 2 there. Okay? Okay. So anyway, I'll get rid of all that stuff there. Okay. So add the exponents. So we're going to have 5 to the 1/2 plus 1/3 power. Now, of course, adding those, right, you need a common denominator. So I'll rewrite this as, let's see here, 5 to the 3/6 plus 2/6, right? Multiply the top and bottom by 2 here, multiply the top and bottom by 3 here, okay? You get the idea. 3/6 plus 2/6 is 5/6. And that's all we have to do. We're supposed to leave it as a rational exponent, so we can stop right here, okay? We don't need to rewrite that in a radical or anything. All right, number 11. So number 11, same directions as number 7. We're going to first rewrite using a rational exponent, and then we will simplify. Okay, so again, I have a root, or 6th root, and a cube root here, so that's going to become 1/6 as the exponent, okay, and then st 1/3. Whoops, 1/3 as an exponent there. Okay. Now at this point, again, we do have kind of some like common bases here, the s to t, the s to t there, but they're both in parentheses, so we need to take care of these exponents here. So this 1/6, that can distribute, okay? Since this is multiplication in here between that s to the 4th and the t to the 9th, we can distribute that 1/6 so it looks more like this. Okay, you see that? So we distributed the 1/6 to both terms in the top, and in the bottom, we'll do the same thing. We'll distribute that 1/3 to the s and to the t. Okay, now what's the exponent when you just have an s or a t by itself? Well, again, like we talked about earlier, those are exponents of 1. So this is s to the 1 to the 1/3. This is t to the 1 to the 1/3 power. Okay? And again, we have power to a power, power to a power, power to a power, power to a power. So we have to multiply those pairs there. And so it's going to be s to the 4 sixths, t to the 9 sixths over 1 times 1/3 is s to the 1/3 and t to the 1/3. Okay? Now, we can simplify these if you want to, using, just like common fraction simplification stuff. But we have a little more simplifying to do with these two numbers and these two numbers, right? Because we're dividing. When we divide, what should we do with our exponents? Well, if you recall up here, right, when we multiplied two numbers that have the same base, we added the exponents. So when we divide two things that have the same base, we subtract the exponents. So this is the same thing as s to the 4/6 minus 1/3 times t to the 9/6 minus 1/3. Okay? So you notice the denominator goes away because we subtracted to simplify there. And now when we actually simplify, and I may have to move this here because I didn't leave myself enough space. Okay, and now when we go to simplify here, we'll have to do this subtraction, right? But to subtract, we're going to change this 1/3 here. We'll multiply by 2, multiply by 2, and so we really end up with 2/6, right? And this 9/6, again, minus 1/3, well, we need a common denominator, so I'll go ahead and just change that to the equivalent to 6 as well. And now I can subtract 4/6 minus 2/6, 2/6. 9/6 minus 2/6, 7/6. This we can still simplify, so we'll go ahead and do that. And our final answer will be s to the 1/3 times t to the 7/6. And there's our answer. Okay? Again, just leaving it in rational exponent form. Now, number 13, the directions change up a little bit. In 13, we are asked to simplify the expression using the properties of nth roots, and then assume all variables positive, and we were supposed to rationalize any irrational denominators, and I'll talk about that here too, if we have any that show up. So, using properties of nth roots. So, you may remember from when you were simplifying square roots, like back in the day, for example, when we had, like, I don't know, square root of 12, as an example, okay? We can make that 12 become 4 times 3, and simplify, to help us simplify it, the square root of 12, right? We can use the fact that 12 is 4 times 3 because 4 is a perfect square. We can then break up, and by the properties of square roots, you can break up this single square root, that's a square root of a product, into a product of two individual square roots, okay? And this is true in general. So that allows us to then take the square root of this 4, which is a perfect square, but the root 3 stays root 3 because we can't simplify that any further, right? So it allows us to simplify the square root of something that otherwise we wouldn't be able to simplify, right? We can't do the square root of 12, I mean, it gives us some crazy decimal. But we can, again, break that into 4 times 3, make it root 4 times root 3, and then finally get our final answer of 2 root 3. So what are we supposed to do here? Well, we could break it down, okay, but let's combine everything together first. So we're going to kind of work backwards here. Here we have a product of radicals, right, like we have right here, and so we can work it backwards to get to one single radical. So we'll just multiply the 36 and the 216, and we're allowed to do that, right, because we're multiplying here, and because it's the same radical, okay? If this was like a 3 here, and that was a 4, we wouldn't be able to do this, okay? Can't combine two different radicals together like that. But since it's a product, and we're multiplying it's the same radical, we'll just multiply the 36 and the 216. Okay, and we get 7,776. And divided by 4th root of 6. Same property can apply here too. Since we are dividing, we can just divide these two numbers, and because they're in the same radical of the 4th root. And so 7,776 divided by 6 is 1,296. Okay? And now we want to try and see if we can simplify this 4th root any. So we're kind of clued in here about like 1,296 is a power of 6, right? Because this is a power of 6, this is a power of 6, this is a power of 6. Okay? So we're going to try and figure out what the power of 6, that 1,296 is. Okay? So, well, let's see here. So it's going to be 6, then 6 squared is 36, then 6 cubed is that 216, and then 6 to the 4th is 1,296. Okay? And so the fourth root of 6 to the fourth will become just 6, and that's our final answer there. Okay, allowing us to simplify. There's other ways we could do this too. For example, we could simplify these individually and then multiply the results and divide the results together as an example. Okay, you really can't simplify the fourth root of 6 at all. There's no like things you can pull out of it. We could rewrite this 36 as 6 squared. Okay, but again, you kind of get stuck because the fourth root of 6 squared doesn't really simplify nicely. So really, the goal here is combine all these things together first, then go about simplifying it. Okay? But sometimes it's helpful to simplify these individually ahead of time, if you can, and then multiply. Why simplify ahead of time? That keeps your numbers kind of small, so it's a little bit easier to do the multiplication and division. Okay? All right, 14. Okay, so here, right, there's nothing for us to multiply together or divide, right? It's already in one radical, just like we had right here. So all that's left for us to do right here is to simplify this thing, okay? So let's do that. So 4,096, I believe that is a power of 2. Let's see here. Let's try 2 to the 7th. Nope, 2 to the 10th. 2 to the 14th. Nope, 2 to the 13th. Nope, 2 to the 12th. There it is. It's 2 to the 12th. Okay, so... Okay, and how do you know that 4,096 is 2 to a power of 12? Well, for me, it's just, you know, a matter of my experience, right? For you guys, it's a matter of kind of like testing things out, right? You know, for example, you can see that 4,096 is divisible by 2. It's even, right? So you can divide by 2. So you just keep dividing by 2 until, you know, you can't divide by 2 anymore and see if that works out that way. But that's kind of, it's a little bit of guess and check with a calculator sometimes, or, you know, until you gain familiarity with recognizing, you know, your powers and stuff like that. Okay, rewrite that as x to the 6th, rewrite this as y to the 8th. So now we have 3 things here. So we could break up this product, whoops, like so. So we can kind of like work with things individually here. Okay, let's start with the fourth root of 2 to the 12th. So, you know, we can kind of think of this a couple different ways, you know, where to start. So I could rewrite this as 2 to the 12 fourths. I know it didn't say to use rational exponents here, but just to kind of illustrate the point, I'm just going to show you using rational exponents, right? The fourth root, the fourth root, right, becomes the denominator of 4, and then the exponent of 12 becomes the numerator of 12 right here. And then you can see it's very easy to simplify, right? What is 12 4 simplified to? It simplifies to 3, which gives us 8, right? So that's a very easy, you know, way to simplify, you know, the two stuff there. Okay. What other options do we have? Well, we could think of this using radicals and say, okay, 2 to the 12th is 2 to the 3rd to the 4th power, right? If I were to multiply that 3 and 4 together, it would give me that 12, so I just break it up. Why did I break it up this way? Because I have a radical of 4, and I have a power of 4 there. So those will exactly cancel, leaving behind a 2 to the 3rd, right? Those will exactly cancel, leaving behind that 2 to the 3rd there, which gives us 8. That's another way to think about it too, okay? And then an alternative to that would be something, because ultimately here, when we take the fourth root, we want to create like things that are powers of 4, so it simplifies nicely. So I could also rewrite that 2 to the 12th as 2 to the 4th times 2 to the 4th times 2 to the 4th, like that, right? 4 plus 4 plus 4 would give us 12, so you break it up that way. And now why is that helpful? Because then, you know, we can say that's 2 times 2 times 2, right? This becomes a 2, this becomes a 2, this becomes a 2, because it's a fourth root of all those things. That's another way to think about it too. Okay, so a couple different ways to look at it. All are kind of helpful here. We're going to use this strategy here for these guys, okay, for the variables. All right, so let me kind of draw this over here. Oops. So now x to the 6th, right? Again, if we want to take the fourth root of x to the 6th, we could rewrite it using rational exponents and simplify it that way, but this said to use radicals, so we're going to stick to what they asked us to do. Okay, so let's break up this x to the 6th so we can simplify it. Well, there it is, right? X to the 6th is the same as x to the 4th times x squared. Okay, and again, I could have done, Mr. Wood, why didn't you do like x times x to the 1, x to the 5th? Well, that's true, right? Would multiply back together to be x to the 6th, but we're trying to take the 4th root here. So we want our exponents to be 4, or multiples of 4, potentially. So that's why we're going to use x to the 4th times x to the 2nd. Okay, this allows us to break up our radical there, and this simplifies just to x, right? And then we still have this left over, though, that doesn't really simplify any further, so we'll just leave it. Maybe I'll put it down here. Okay, and then our last one here, okay, same kind of idea, right? We want to break up that y to the 8th so that it's like just y to the 4ths, so we can try and simplify that. Well, the y to the 8th breaks up nicely, right? We can make it y to the 4 times y to the 4, which is 4th root of y to the 4 times 4th root of y to the 4, and those both simplify just to y. So now let's put all these pieces together here, and we'll end up with 8x y squared. Those are all the parts that we're able to simplify precisely out of the 4th root. We still have this 4th root left over, so we'll write that at the end. Okay, if we had had any leftovers from the y's, for example, let's say we still had like a 4th root of y here, that y would go in with the x right there. Okay, you can recombine all those 4th root of y's back together. Same thing here. If there was a number in here, like we still had the 4th root of 3 for some reason here, then you would bring that 3 back inside, putting it in front of the x like that. Okay, so that's simplifying with the radicals. Let me know if you have any questions on that. Still. Okay, next, for 11-3, we were asked to simply solve the equation. That's it, okay? So the key thing to remember here, so you guys already have the basic understanding about solving equations, right? If you want to solve an equation, you need to get the x by itself. The problem is here, though, we have two different x's, and one is in square root, and one is not. So we cannot just get these two things together. I also cannot break this up and say, oh, it's just the square root of x plus the square root of 3. This is not a property of radicals, okay? So if it was a product, if it was root x times 3, then yes, it would equal root x times root 3, okay? But root x plus 3 does not equal root x plus root 3, okay? Not in general. There are some cases where it's true, but in general, we can't use that property, right? If x were 0, it would be true, but in general, we can't use that property, okay? So anyway, what do we do here? We need to eliminate the square root. And what eliminates a square root? Well, squaring. And of course, in an equation, right, if you do it to one side, you've got to square the other side too, the entire side. So when I square a square root, we're left with just x plus 3 right here. When I square x plus 1, it's equal to x squared plus 1 squared, right? No, wrong. X plus 1 squared is x plus 1 times x plus 1, right? When you square something, you multiply by itself. And that multiplies out to be x squared plus 2x plus 1. Okay, now our square root equation has changed to a quadratic equation. Womp womp, so we have to solve it using our quadratic rules. So we'll try getting everything to one side, so it's equal to 0. And we'll have 0 equals x squared plus x minus 2. And now we'll see if this thing can factor. Hopefully it can. Otherwise, we're going to use that quadratic formula. Let's see, I need two numbers that multiply to -2 and add to make a positive 1. That would be positive 2 and -1. And so we'll say x plus 2 equals 0 using the zero product property. Set each factor equal to 0 there. And we'll say x equals -2 and x equals 1. Okay, and voila, there are your answers. The only thing we have to keep an eye out for is checking them back in the original equation to make sure that they actually work. So let's see, if I plug -2 in for x, I'll get -2 plus 3, which is 1. Square root of 1 is 1. -2 plus 1 is -1. Ooh, this one does not work. Okay, so negative 2 does not work. Let's plug in 1. 1 plus 3 is square root of 4. Square root of 4 is 2. 1 plus 1 is 2. Check. So this one does work. So that's our only actual solution. This negative 2, when you plug it back in, does not work. All right, let's try number 5. Same situation, right? Except now we have a rational exponent, but we can get rid of that rational exponent. Anytime you have a rational exponent here, you would just raise it to the reciprocal power. So we'll raise it here to the reciprocal power. How do I know it's going to be the reciprocal? Well, again, to eliminate a rational exponent, you want to use another exponent. Okay? We want to eliminate it, and when we raise to another exponent, we're going to be multiplying. So to eliminate using multiplication, you multiply by the reciprocal, right? So if I have, 1/3 x, I can multiply by 3 over 1 to eliminate that 1/3, right? Same thing's true with the powers there. So I use 2 over 1, okay? Remember that 1/2 is just a square root, so we can also just, we're really just squaring here too. Okay, so we end up with x plus 4 here, and then 6 to the 2 is, 36. And you just subtract 4 on both sides, and voila, 32 is your answer. Again, check it back in, plug 32 in here, plus 4 would give you 36. 36 to the 1/2 power would give you 6, which is what we had initially there, so 32 works. Okay, last one, number 9. Okay, we have a cube root, right? And the x is inside that cube root. So we got to eliminate stuff, get the x by itself here. What I would discourage you from doing, right? Do not cube root first, okay? Do not cube root first. You want to isolate this radical. Get the radical by itself first, then cube root. So we'll subtract 5 on both sides first here. Divide both sides by -1 to cancel out the negatives there. So we'll have the cube root of x minus 4 equals positive 3. Now, we want to eliminate that cube root. What undoes a cube? Well, cubing. Or what undoes a cube root is cubing. So we'll cube both sides. We're left with x minus 4 equals, and then 3 to the 3rd is 27. And now we just add 4 to both sides, and you get 31. And there's your final answer. We can check it back up in the equation here. 31 take away 4 is 27. The cube root of 27 is 3. 5 minus 3 is 2. Check. It works. All right. Hope that helps. Let me know if you have any further questions on this stuff. I'll be happy to do some other examples. If you want to pick some out of the book, just let me know. Thanks, guys. Bye.